So it's a great pleasure to introduce Charles Epstein from the Flatiron Institute, and here we have the title, beautiful title, Fredholm, Sommerfeld, Carlos, and Charlie. Right?
Well, it's a great pleasure to be here, and a great honor to speak in Carlos' 70th birthday. It's a little astonishing. In my recollection, okay, it's not cooperating. This is Carlos. I now discovered something, that the full screen is bigger than the full screen. Let's see what I should do here. Can I make it a little smaller? What if I exit full screen? That's too small. Okay. Well, we'll find out what happens. So, happy birthday, Carlos. That's Washington Square. I don't know if you can stand still for that long anymore in Washington Square. It's become a little dangerous. So I want to first of all thank the people I've worked with. So I was a pure mathematics student at Courant and didn't take any applied courses at all in 4 years. And over the course of time, I discovered that there was something missing in my life. And I started to work on much more applied problems. And now I work on, I don't want to claim to be an applied mathematician in any serious sense of the word, but the problems I work on mostly come from the applied side. And these are the people who have made it all possible for me, particularly Manas Rach, Shidong Zhang, and of course Leslie Greengard, who is the boss. Okay, so I have this very distinct recollection that when we were graduate students, so Carlos was working in inverse scattering, which was a popular thing to do at the time. And he was working on the Boussinesq equation, as we all know now. And we know that there's a school of inverse scattering theory that was popular in those days that I think has somewhat fallen out of favor, that involved solving integral equations. Fadeev, Marchenko, Zakharov, Shabbat, these guys. And I can remember a day when Carlos told me that he had proved that his integral equation had no null space. It was a big day, because it meant that that inverse scattering transform actually could be inverted, because you could then solve the integral equation. Now, I have to say, this is just for everybody's sake. So if we start out with an integral kernel, it defines a compact operator. The equation identity plus Ku equals F is called Fredholm equation of second kind. Such an equation has Fredholm index 0, so it means the dimension of the null space is equal to the codimension of the range. And so it's solvable only if the null space is trivial for all F. So yes, I remember when this happened. So I didn't appreciate it at all at the time. I didn't care about Fredholm equations. I didn't know anything about integral equations. And then, one day, so when you're not watching, these things you paid no attention to suddenly have dominated your entire life for decades. So that's where I am today. I'd like to talk about something called radiation conditions and uniqueness for the PDEs that are connected to the integral equations. And I have to admit that ultimately the results I'm going to talk about are really not my results. They're really mostly the results of people in the 1990s. But we'll get to that. Okay, so the simplest example, and I'm only going to talk today about acoustic scattering, and it's going to be, I have to apologize, it's linear. And this was always a problem at the Courant for me, because there was a saying at the Courant attributed to Peter Lax that linearity breeds contempt. Although you also have to look carefully at Peter Lax's oeuvre, you'll find that at least 50% of it is on linear equations. So he could deal with it. I could deal with it too. So I'm going to talk about acoustic scattering from boundaries of obstacles. We consider the time harmonic case, so the time dependence is just e to the minus I omega t. So in the end, you're just solving the Helmholtz equation. That Laplacian plus k squared u is 0, where the wave number k is just the frequency in time divided by the wave speed. For a simple example of such a problem, we have a bounded domain in R3 with a smooth connected boundary. We have some incoming wave, which is the solution to the Helmholtz equation. It's defined near the boundary. And then we define the scattered wave. And the whole physical process of scattering is just the boundary condition, which is sort of characteristic of almost all of physics, that all the physics is in the boundary condition for the most part. So, in the end, we define a total field, which is the incoming wave plus the scattered field. And where the scattered field comes from is that the incoming field does not satisfy the boundary condition. So if we have what's called sound soft scattering, then we want the total field to vanish on the boundary. Or if we have what's called sound hard scattering, we want the normal derivative of the total field to vanish on the boundary. So just to have something in mind, a typical incoming field is just a plane wave. Okay, let's see what happens now. So, because the region is not, the complementary region of D, which is where we're going to solve this equation, is unbounded, and minus k squared belongs to the spectrum of the operator with either Neumann or Dirichlet boundary conditions, we don't really have a well-defined solution. We have to pick a solution by specifying the asymptotic behavior at infinity. So another reason you can see this must be true is that there's sort of two equally good fundamental solutions for this operator, given by that expression there, where I can take a plus or a minus ik. So we observe the following thing. If we take that fundamental solution and we apply this operator, d by dr, minus or plus ik to it, it decays like 1 over r squared, whereas this decayed like 1 over r. So we improve the decay if we apply that so-called radiation operator. And this was Sommerfeld's observation, and he said, okay, we'll define this outgoing radiation condition by this condition here, that dr minus IKU of r eta, eta is just a point on the sphere, should be big O of r to the minus 2. And then some years later, Relic actually proved that that does define a unique solution, and with whatever boundary conditions you specify, whatever good boundary conditions. And in fact, eventually people realized that this was a rather demanding condition, and actually if the radiation operator applied to you vanishes any faster than 1 over r, then you still get a unique solution. Okay, so how do we actually solve a scattering problem? So we look for the solution, let's say with Neumann boundary conditions. We have an incoming field. We want to find an outgoing solution, so it's supposed to satisfy the Helmholtz equation, and it has this inhomogeneous boundary condition. So what we do is we say, okay, let's write it in terms of the fundamental solution, as in terms of a density on the boundary of the region. We take the normal derivative, we take the limit as we go out to the boundary, we use this classical jump formula, we get this very nice formula, which is that the normal derivative, depending upon whether you come from the inside or the outside of the region, you get a different identity term here, minus or plus sigma over 2, plus a certain operator acting on the boundary. And while this operator looks like it has a very singular kernel, in fact, because you're restricting both variables to lie on the boundary, this is actually a weakly singular kernel, and this defines a compact operator. So once again, this will be a Fredholm equation down here of index 0. Okay, so the limit again, the plus and the minus refers to whether I come from the outside or the inside. Okay, so as I say, the operator, the kernel restricted to the boundary, it's a compact operator. So once again, we have a Fredholm equation of the second kind. We're interested in the exterior, so we're interested in the null space of this map. Sigma goes to minus sigma over 2 plus the kernel applied on the boundary. And I'm being very casual here. If you really want to talk about being Fredholm, you do have to talk about it acting on a function space. So it turns out not to matter very much which function space you work with. But let's just say we'll talk about C alpha functions. It's very classical in this field. Kellogg was a fan of C alpha functions. Okay, so suppose that for a real K, there's a sigma that satisfies that it's in the kernel. So it's in this kernel of that operator. And what I'm going to do is I'm going to let V be the single layer potential, just that operator applied to my density. And I'm going to let V be the single layer potential of sigma. It solves the Helmholtz equation anywhere off of the boundary. And its normal derivatives from the exterior would have to vanish on boundary D. That's the assumption that it's in the null space. So, okay, it's clearly outgoing. And so we have this classical theorem of Relic that says if V restricted to the boundary, okay, so it's outgoing. And so clearly it's got to be 0, because Relic proved this theorem that says if you have an outgoing solution, the normal derivatives vanish, it's identically 0. Okay, so that's the first observation. So we use this great PDE uniqueness theorem that says we've written down this layer potential, and because it's got near zero normal derivative and it's outgoing, it's got to be zero. So now, Relich's theorem says, well, V restricted to this complementary domain is zero. And it's easy to see that a single layer potential is continuous across the boundary. Okay, so that means that V restricted to the domain D is an eigenfunction of the Dirichlet Laplacian. Okay, we're going to get some messages, I don't know. Okay, such functions exist, and in fact, there's a discrete set, K sub j, for which this operator, M sub k, does have a null space of real K sub j's. Okay, well, what about if K is not real? Well, the imaginary part of K is greater than 0. The Dirichlet spectrum of D lies in 0, infinity, so V would have to be an L2 solution of that in the exterior domain, but we can easily see that such things don't exist. It would have to decay exponentially at infinity. So that's easy to prove it's 0. But then we're left with one more interesting case, which is the imaginary part is less than 0. Then we have a solution to the Helmholtz equation in the exterior domain, which has this representation as a single layer potential, and its normal derivative is 0. That's still true because it's in the null space of M sub k. And it's exponentially growing at infinity, and you might say, well, that's not very interesting. But in fact, it's extremely interesting because that means that this k is a resonance of this problem, that the scattering operator for this problem has a pole at k. And Lax and Phillips tell us that this condition, that U is represented as a single layer potential, is exactly the condition to be a scattering resonance. So this is somehow telling us that the null spaces of these integral operators are rather interesting. It also tells us something else, which is that to understand them, we have to understand a PDE problem on one side and a PDE problem on the other side. Both sides are important for understanding the null space of an integral operator on a boundary. Okay, I think I just said everything that's on this slide. Right? The integral representation, it's important to remember, integral representation doesn't know which side of the boundary you're working on. It's solving a problem on either side, and it actually says something interesting about either side. Okay, I picked a bad representation on purpose. I wanted to demonstrate the interest in the null space of this operator. Numerical analysts would never do that because they know that they can change the representation a little bit and get something which is actually invertible for all real k's, or all k's in their upper half space, which is mostly what they're interested in. But then they don't get to see all those interesting phenomena. Okay, now the actual problem I'm interested in is not the Dirichlet problem. I'm interested in something called the transmission problem. So here, I let gamma be, again, a smooth compact surface, which is the boundary of omega minus, the bounded component, and omega plus, the unbounded component. And we have a wave coming in from the we have an exterior wave number, k plus, an interior wave number, k minus. They're usually different. We're interested to see how the wave interacts with this, what we call transparent obstacle. It's an obstacle because it has a different wave number from the ambient space. So again, we'll have an incoming field, which we'll just assume solves the equation Laplacian plus k plus squared u in is 0 in some neighborhood of the boundary in the exterior region. And then what we do, we look for the scattering problems defined by this. We look for u plus and minus, defined in omega plus and minus, that satisfy the right PDE, the correct version of Helmholtz equation. And they satisfy what are called transmission boundary conditions. So that is, the total field in the outside, which is the u incoming plus u plus, restricted to the boundary, should be the field in the interior. And the normal derivatives should match up with you can allow yourself a multiplier if you want. And we can rewrite that as the difference across the boundary is given by this incoming wave, and the difference of the normal derivatives across the boundary is the incoming wave. Okay, so the incoming wave defies jumps in u plus minus. Okay, for the rest of the talk, we'll just set mu equal to 1, because it doesn't really interest me that much. Okay, so we do the same thing. It's kind of a boring subject. We write down the layer potential representation. So here we have a single layer and a double layer. The double layer is obtained by differentiating the kernel in the y variable, in the incoming variable. So we haven't done anything to it in the x variable, so it's still a solution of the equation in the x variable. It's the same fundamental solution. We restrict the representation to the boundary. We use the standard jump relations. We take the difference, and we obtain these integral equations on the boundary for our unknown densities. Now we have two. We have a sigma and a tau. So we have a system of two equations and two unknowns. They start out with an identity term, and then we have all these integral operators on the boundary. Once again, it so happens that all of those integral operators, which are differences of kernels, define compact maps. So it's actually easy to see for that term, and that term. This one term here where I've taken the normal derivative of a normal derivative, that's a pretty singular kernel. But because I've taken the difference of two such kernels, the principal singularities cancel, and again it defines a compact operator. So everything is working in our favor, and again, they're compact acting on L2 of the boundary, C alpha of the boundary, even though this is strongly singular. So these equations are again Fredholm of second kind, and uniqueness will imply solvability. Okay.
How do you pick the U naught on the left-hand side?
How do I pick?
Is it a general function, or you have?
This just comes from my incoming wave. I can just again take a plane wave. Any solution of the PDE in the exterior you can stick in there. Because it's a compact boundary, it doesn't matter very much, because you're going to restrict it to the boundary. It's going to be a real analytic function on the boundary anyway. So, I mean, typical examples are you take plane waves. Other people, you might take a fundamental solution in the exterior and use that as the incoming wave.
You want to solve this for arbitrary U naughts.
Yeah, for pretty, but the theory about integral equations doesn't really care too much about that. It's all just, in the end, restricted to the boundary, and then it's just functional analysis. You just have to pick a function space in which everything works. Everything works fine for you. The reason being that these are all classical pseudo-differential operators. So whatever function space, whatever reasonable function space you pick, they define compact maps. So at this point, this isn't an issue. It'll be an issue later in the talk. We can get back to it later on. Okay, so we saw that when we were talking about uniqueness for the simple Dirichlet problem, we still had to deal with what I would call the problem we're interested in, the exterior Dirichlet problem, and a complementary problem. We were actually talking about the exterior Neumann problem. The complementary problem was the interior Dirichlet problem. So again, whenever you have these integral equation representations for a solution, you always have the problem you're interested in, which you pick the representation for, and then you have this complementary problem. So it turns out that for a transmission problem, the complementary problem is the same problem where you just interchange which wave number goes with which domain. So you take the k minus, you use it in the exterior, the k plus, you use it in the interior. Right, because the argument is the same as I gave before. You say, suppose I have a null space for this system of equations. Well, then it means I have a solution to the transmission problem with homogeneous boundary data, with the jumps are zero. Then you have some PDE uniqueness theorem, which is just basically integrating by parts, and you demonstrate that the only such possibility is that it's zero. So that tells you that the solution to the problem you were looking at would be zero if the integral representation had a null space. And then you say, okay, let's interchange what I mean by the inside and the outside. And then I apply the same theorem, and it says, oh, well, that one's also zero. And then I say, okay, well, then I can just compute what sigma and tau are by using the jumps in the normal derivatives. Because the inside and the outside are both zero, the jumps in the normal derivatives are zero, that means sigma and tau are both zero. So then I proved the integral equation has a unique solution. Okay, so once again, you can use your favorite choices of spaces, L2 plus L2 of the boundary, C alpha plus C alpha of the boundary. Actually, the natural choice for this particular problem is H1 half of the boundary plus H minus 1 half of the boundary, because one of the terms is the value of the function, the other term is the normal derivative. And if you work your way through it, you'll see that actually it's a compact map. Those operators over there define a compact map from this space to itself. Okay, so that's the standard transmission problem. So what about Relich's uniqueness theorem? So this is Franz Relich, who always looks so happy in his photo, even though he had to leave Göttingen because the Nazis made him go. So all the uniqueness results so far boil down to this Relich theorem. And the proof of this theorem uses in a very essential way that a neighborhood of infinity is just free space. And it's just the equation in a neighborhood of infinity is just the constant coefficient Helmholtz equation. And so what happens, the way the argument works is that using the radiation condition, I can prove that U is given by Green's formula, where I just integrate over the boundary of some sphere. Then I can use that I use the fact that this kernel has an expansion in terms of Bessel functions and spherical harmonics to prove that the solution U actually has a convergent expansion in the exterior of a large ball. Then what I say is, well, okay, the coefficients of this expansion, F1, F2, are actually determined all by the first coefficient, F0. And if F0 is 0, then U actually vanishes in the exterior of the ball. Now, once U vanishes in the exterior of the ball, then what I have to do is I have to use a slightly, in this case, I actually don't have to do anything hard, because it's very obvious from the representation formula that the solution is real analytic. So as soon as it vanishes in an open set, it's identically 0 in the connected component that contains that open set. But I can use the same argument for all kinds of situations. I could have a potential instead of an obstacle. And then I have to use a harder theorem, which is this unique continuation theorem for elliptic equations that says if I have a solution of an elliptic equation that vanishes in an open set, it's identically 0. Second order elliptic equation. Okay. So I think what I'm doing here, for some reason I decided to prove this, that this is the proof. I say, okay, this is 0 because the thing is the solution of the equation. I multiply it by U bar, I integrate it over the exterior region intersected with a large ball, I integrate by parts, I get this term here. You think, oh, that term's the important term, but actually that term's a nuisance in this argument. And you say, okay, we're going to take we use the radiation condition, which tells us that the imaginary part of this right-hand side here is just this one term, which is essentially k times the modulus of U squared over the sphere, plus something with order r to the minus delta because of the radiation condition. So we see that if it satisfies the radiation condition, the limit of the integral over that sphere goes to 0. And so we conclude that the limit, on the other hand, the limit of the integral is just the integral of that initial term in the asymptotic expansion. And so again, that must be 0. And so here we've seen that for a compact scatterer, we can prove the uniqueness theorem for our Fredholm equation. Okay, so everything I've discussed now has been known for 50 or maybe 100 years. So the interesting thing is, and I think we saw this in the last talk, it's not very hard to find problems in mathematical physics that are very natural problems that people feel like they solve them all the time. And in fact, very little is actually known about them. And that was the case here. So the work I want to talk about has to do with acoustic waveguides. And they again are described by some variant of the Helmholtz equation. And basically, what are waveguides? Well, let's talk about the electrical case. I'm going to only talk about the acoustic case. But in the electrical case, it's easier to describe. We all know that if you have low frequency electricity, you can usually describe it as passing through wires. And you can talk about current and voltage. And you don't have to worry about magnetic fields. And just everything's fine. But then you reach a certain point where the frequency gets to be too high. And that description no longer makes any sense. And this was apparent already in the early 1900s. And one of the great exponents of this was Oliver Heaviside, one of the great characters of 20th century physics and math. He had like an 8th grade education. He bought a copy of Maxwell's Treatise of Electricity and Magnetism and realized he had some things he needed to learn, but he was going to learn them. He became one of the world's greatest experts on it. And one of the things he did along the way was he invented the coaxial cable, which was important for transatlantic transmission of telephone signals. Very well worth reading his Wikipedia page. Okay, so this is what I want to talk about. I'm going to talk about the problem of scattering from open waveguides. So these are waveguides where they don't have a hard edge. So what it is basically is I have a large medium, and in this medium I have embedded channels in which the sound speed is different. But there's no hard separation between the channels and the surrounding space. Now, these don't come up that much in acoustics. They come up all the time in photonics. So when you build optical circuits on chips, this is essentially what you're doing. Then you really have to talk about Maxwell's equations, so we're not going to talk about that, but that's more the application than acoustics. Okay, so we have an ambient wave number, which I call K1, and in the channels, I have different wave numbers. And then we also allow ourselves a little compact interaction zone. Okay, so we're going to talk about propagation of waves. It's described by the same equation as before, but now I have a potential. The potential is going to be 0 outside a compact set, except for neighborhoods of these rays going out to infinity. So I assume it's compactly supported in a neighborhood of the ray. And we'll again assume the solution is an H2 loc, which is just this condition about it should be continuous, and its first derivative should be continuous across the interfaces if there are any. Okay, and as before, we're going to have some kind of incoming wave and a scattered wave. The incoming waves are a little harder to describe here because infinity is harder to describe here. The scattered wave is the scattered field, and it has to satisfy some kind of outgoing radiation condition. Okay, so this is a sort of general class of problems, and we developed a general sort of method. We call them decomposable. So now I want to emphasize, the important thing about this problem, which makes it not the problem that I talked about, is that the scatterers extend out to infinity. So there is no neighborhood of infinity where the equation is just the flat space Helmholtz equation. No matter how far out you go, you still have some perturbations. But on the other hand, those perturbations are rather confined, and their dependence on the variables within the channel is very simple. They don't depend upon the radial variable, only the transverse variable. Okay, so we'll say we can divide space into a collection of sectors that look like cones out after some point, and compact sets where they fit together. In each conical set, we have an equation that is just the Laplacian plus the background field plus a perturbation, Q sub j, which is compactly supported, and only a function of the transverse variables in that set, which is some neighborhood of the ray. Now, we're going to assume that we can find fundamental solutions for each of these operators, defined in all of R2 by that formula. So this is what you call a bi-infinite waveguide. It goes from minus infinity to plus infinity, and it only depends upon the transverse variable. Okay, so this is like sort of when you take PDE and they say, we're going to use the method of fundamental solutions to solve this PDE. All you have to do is write down the fundamental solution, for, incorporating the Dirichlet condition or whatever, and you can write down the answer to the equation. And eventually you come to realize that that's just as hard as the original problem. That doesn't look any easier. But here, in fact, this whole idea of using layer potentials is that, well, you don't actually have to solve the whole problem. You don't actually have to write down the boundary conditions. You have to get a way of generating solutions to the equation in the part of space that you want them to be defined in. And that's sort of how I came upon this. So what we're going to do is we're going to, we have an incoming field. It's going to define data on all of the boundaries. The details of how exactly this is done depends on the data, and it depends on the boundaries. And I'm not going to go into any great detail here. We're going to use our fundamental solutions to write down the solution to our equation in each of the different regions in terms of a different fundamental solution, just as we did before. Now, it's not actually obvious that you can do this in the unbounded sectors. So there is a radiation condition that I'm going to talk about soon, and it's a consequence of the radiation condition that you have such a representation. Now, it will also require that the sources themselves satisfy certain conditions. So this is one of these funny things. You're looking in the literature, you're sure somebody's thought about this. The question is, what if I write down that formula? What do I need to know about the sources, sigma and tau, to know that the solution is outgoing in the sector? I never saw a theorem in the literature, but you'd think it's a pretty natural question. Okay. So before we recast the scattering problem as a transmission problem, we restrict everything to the boundary. We obtain integral equations. They're defined on a collection of rays and compact piecewise smooth curves. Turns out, people who work in integral equations will raise their hand and say, well, what do you do where all those curves come together and you have triple intersections? The genius people I work with know how to deal with that. We don't worry about that at all. However, okay, here's a real problem. The non-compactness of the boundaries of the sectors would appear to make it impractical to solve those equations because the distance to the 3/2 power 1 over the distance to the 1/2 power, they're not going to decay fast at all. So maybe you worry about that. But just sort of simultaneously to my working out this way of solving transmission problems, one of my colleagues, Shidong Zhang, said, there's this great trick that I found in the literature by this Lu and Qian. They have this idea of complexifying the curve on which you solve the integral equation. So you're solving the equation along a line that goes out to infinity. And they just say, well, just move it up into the complex plane a little over there, and move it down a little over there. It turns out if you pick the complexification correctly, what was oscillation going out, and you have a specific kind of oscillation going out, because that's what outgoing means. When you complexify it, it becomes exponential decay. And that, in the end, is what allows us to actually solve these equations. But I don't have time to talk about that in any kind of detail today, but I just thought I would say a word about it. Okay, so the simplest open waveguide problem in 2D, you just put a bi-infinite rectangular channel with a different isotropic material. So it's governed by an equation like that. So the potential only depends on the x2 variable. It's compactly supported between minus d and d. In fact, for the rest of the talk, we're just going to talk about where q is just a k2 squared minus k1 squared. So it's a piecewise constant problem. Now, for such an operator, you can actually compute the fundamental solution as well as you want, and then it allows you to solve the next simplest problem. The next simplest problem, though, is the first problem for which you can't write down the answer. Okay. Okay, so what makes these problems interesting and very different from the compact scattering problem is the existence of traveling wave solutions. So if Q is a piecewise continuous function with bounded support, then if it's sufficiently positive, there are finitely many energies so that, and that should be d by dx2 squared plus Q, Vj squared equals Ej squared, has an L2 solution. So, in fact, they're exponentially decaying solutions. And from such a solution, we construct a traveling wave. We multiply by the right exponential factor, where Cj is given by that formula. And that gives a solution to the PDE, which has the unfortunate feature that it does not decay as you go out the x1 axis in either direction. So it's kind of cluing you into the fact that Sommerfeld's condition is not going to work anymore. Okay, so it's one of these problems. I worked on it for a long time. And then at some point, I got to this point where I want to prove uniqueness. I haven't even explained to you yet why I can get Fredholm equations of second kind for which I need to prove uniqueness. And then I thought I'll just look in the literature and find the standard radiation condition. And what I discovered was that there was no discussion of this question at all. People have worked on this problem for 50, 75 years. And somehow or the other were never bothered by the fact that they didn't know the right condition for the problem to have a unique solution. They just went ahead. In fact, for the most part, they ignored the existence of the radiation in this problem. They just pretended everything was traveling down the channels. It was a real don't ask, don't tell situation. Okay, so what are the issues? The outgoing solutions don't need to decay. It's not clear what we mean by the radial frequency. And Relish's uniqueness argument obviously doesn't apply because there's no way you can get away from the scatterer. No matter how far you go out, you're still within the support of the scatterer. Okay, so as I say, as far as I know, up until about 2022, nobody had actually really even asked this question, or they only asked it very quietly to themselves. Okay, so I was working on this, and I started finding, various theorems, and I realized that once the scatterer is not compactly supported, this question of uniqueness becomes very, very difficult. And then I had this epiphany that there's this giant field of n-body Schrodinger operators. And they study operators which are sums of Laplacians and different collections of variables plus potentials which are functions of the difference of the variables. And they have exactly the same feature as my problem, which is that they're potentials that do not vanish as you go out to infinity along certain directions, and they depend upon variables in a very restricted way. And I thought to myself, if they know how to do this, they know how to do my problem too. Because this problem is obviously harder. And sure enough, this was studied extensively in the 70s, 80s by Barry Simon, Fritz, Herbst, Perry, long list of people, way too long to list. And in particular, Isozaki. And Isozaki actually found the correct radiation condition. So I'll get to that in a minute. So there's this other object of interest called the limiting absorption principle, which is that we want to solve a problem h plus k squared or h minus k squared, u equals f. And we know this is a tricky thing because we're on the spectrum. And then the physicist said, well, you know, this is kind of an idealization, because in any real physical system there's dissipation. So that means you add a little I delta and you off the spectrum. You're in the resolvent set. There's a well-defined solution. And the question is, can I take the limit of those solutions as delta goes to 0? And the answer is yes, in lots and lots of cases. This is called the limiting absorption principle. And it's intimately connected to the radiation condition, because in fact, you can take a limit from above or below, and you get different solutions. And one solution is outgoing, and one solution is the opposite, it's incoming. So, and this is all work, I guess. Muir introduced this thing called the positive commutator argument, which involves studying the commutator of H with this radial derivative. And the whole subject actually devolves around this work. And then there are Carl-Lemon estimates, which are too hard to discuss. Okay, in 1992, Isozaki published a paper called A Generalization of the Radiation Condition for Sommerfeld's N-body, for N-body Schrödinger operators. And it does exactly that. And it uses a partial microlocalization in infinity, which I'll talk about in a little bit, relies heavily on global commutator estimates. So as I understand it, Richard Melrose heard this talk, and he thought, this is crazy. I don't understand this. There must be some better explanation for all this. And he sat down and he worked on this problem for a couple of years, and he published this really remarkable paper in 1994, introducing what's called the scattering calculus. And he introduced something called the scattering wavefront set. And what he realized is that while this is an elliptic equation, Laplacian plus k squared u equals 0, at infinity, it actually behaves like a hyperbolic equation. And there is a reasonable notion of propagation of singularities. And he described the propagation of singularities in very precise terms and quantified it in very precise terms in such a way that you could really understand the Sommerfeld radiation condition, the fact that there's a critical decay rate. And that was as far as Melrose decided he wanted to go. But then he had a brilliant student, Andras Vashi, who in 1997 wrote a thesis where he uses Melrose's framework, extends Isozaki's results to a class of operators that actually includes open waveguides. And he did the analysis of what's called the three-body problem. And he wrote a beautiful article in the Asterisk, Propagation of Singularities in Three-Body Scattering. Okay, what makes it the three-body problem? For me, why is a waveguide a three-body problem? It's because in a three-body problem, the channels don't intersect at infinity. You have three independent channels at infinity. You don't have to worry about the hardest part of this problem for the Schrödinger equation, which is the interaction of the channels. So this difficulty is removed from us. Okay, so I want to discuss these radiation conditions for waveguides. So the general case, and I'll just talk about the general case, but maybe we'll restrict to 2 dimensions. So we pick a collection of directions. If omega denotes a point on the unit circle, we're interested in the behavior of our solution, u of r omega as r goes to infinity. If omega is not one of the ends of the channels, it seems reasonable to expect that the Sommerfeld radiation condition should be just fine. In fact, right, so the dr minus IKU, big O of r to the minus a half plus delta is just fine. Along a waveguide, the solution might include waveguide modes that behave like that. So the Sommerfeld condition obviously can't apply. So I'd say it does suffice to use Sommerfeld away from the channel ends. So there are 2 principal ideas here. The first is that it is possible to make sense of the notion of radial frequency at infinity for solutions to these sorts of problems. And we only need to distinguish between things that have positive and negative radial frequency. Now that's not obvious from Sommerfeld's condition. Sommerfeld's condition looks like it's a very precise statement, but it turns out that such a precise statement is not needed. You just need to distinguish between things going that way and things going that way. And there is a critical rate of decay which characterizes outgoing solutions. And anything that decays faster than that is actually identically 0. Okay, so this is how it all works. I'll try to make sense out of it. So we actually could adapt Isozaki's ideas, and in fact we could, this case is a little bit simpler because in their case, the ends of the channels are never zero-dimensional. They're always at least circles and usually spheres or something. For us, because we're just looking in the neighborhood of a ray, everything is zero-dimensional at infinity. So what we do is we pick, first of all, a conical bump function. So we're going to just look near the end of the channel. So it's 1 for the. I'm not sure whether this numerology is correct, but so we have a solution to we have a formal solution to the equation. So that is, we apply the operator, we get something Schwartz class. We compute the distributional Fourier transform of this function. So we restrict it to the conical region and we compute its Fourier transform. Now, this thing doesn't necessarily decay very well. So it doesn't have a Fourier transform in the L2 sense, but it has a Fourier transform as a tempered distribution. And that's fine with us. And in fact, not only does it have a Fourier transform as tempered distribution, but because the thing is always smooth, because it's a solution of an elliptic equation, it's actually rapidly decreasing at infinity. Okay, so this is the Fourier transform of U localized near a particular direction at infinity. Okay, now this is what we do. We need to make sense out of the radial frequency at infinity. So we pick a cutoff function, so it's going to be 0 for t a little bigger than 0, and 1 for t a little bit less than that same number, but still a little bigger than 0. And we have this very unpleasant looking thing, which I will explain. So here's our conically localized Fourier transform. Here is this cutoff function evaluated at omega dot xc. So the outgoing variable here is r omega. So this is the direction in the outgoing variable. So omega dot c is actually the symbol of the operator d by dr. So that's how we're localizing in the radial direction, the frequency in the radial direction. We take the inverse Fourier transform and then we localize in the same cone, and what we want is for it to decay a little like r to the half minus some positive number times an L2 function. So that's where we see the critical rate of decay. So we want to see exactly this rate of decay. If this is true, then we say U is outgoing in a neighborhood of infinity. Okay, so this condition that this quantity belongs to r to the half minus a to L2, that's the same as the Sommerfeld radiation condition. So those numbers are not accidentally the same. So for example, just compute an example. If we have a waveguide mode, so it's e to the I theta x1, where the waveguide lies along the x1 axis, and I restrict it. The conical cutoff is I just have to restrict it to the positive x1 axis. I compute the Fourier transform, and what I get is essentially the delta function in the xc1 in the waveguide frequency, at the waveguide frequency, times the Fourier transform of the transverse part, which is a Schwartz class function. Okay? Plus something which is a Schwartz class function. It's very easy to see that this satisfies Isozaki's conditions. You just compute the inverse Fourier transform and you see, for example, if you go right down the channel when you compute the inverse Fourier transform, you get 0. And if you're a little bit off the center of the channel, you get something Schwartz class. So it's very easy to see that it satisfies this. Okay, so as explained in this work of Melrose and Vashi, this rate of decay is a sharp dividing line between outgoing and incoming solutions. Vashi proved that the outgoing solution to this equation is unique, and the limiting absorption principle applies, and the limiting absorption solution is the outgoing solution. Okay, now, how much time do I actually have?
You have, started a little late, so you have like 10, 15 minutes.
Okay. Okay. All right, so I want to explain a little bit of the idea of Melrose's scattering calculus. So really the question was, we have these conditions, they're very sharp, but why are they true? And in particular, Isozaki's condition, it looks so flabby. Isozaki's condition just says the radial frequency just has to be of the right sign to define something outgoing. It doesn't have to be at a particular frequency. It has to be of the right sign. Why is that enough? So Melrose thought to himself, well, let's see if we can explain this. So being Melrose, the first thing he did was he compacted RD radially. So he put a point at infinity for each direction going out to infinity. So you get a sphere at infinity. You have coordinates. If those are coordinates on the sphere, you let x be 1 over r. Then x eta are coordinates for a neighborhood of infinity. When you write down the standard Euclidean vector fields, you get x squared d by dx. That's actually d by dr. And these are just other coordinate vector fields. The ones tangent to the sphere vanish like x. The one normal to the sphere vanishes like x squared. Okay. Now, again, you can extend all these sort of geometric structures to infinity. Onto this compactified space, you get a scattering cotangent bundle. Those are the basis forms. They look, well, you might say, well, those are singular at x equal to 0. Well, who tells you to set x equal to 0? They're just really formal. Okay, and we can define a boundary symbol for the operator, which is a function on this compactified cotangent bundle. The symbol of Laplacian plus k squared is k squared minus mod of zeta squared. So the thing is that the zeroth order term appears in the symbol at infinity. That's sort of what distinguishes it from the classical symbol. It's not elliptic. There's a characteristic variety at infinity. It looks like this. X is 0, eta is a point on the sphere, and mod c squared is equal to mod k squared. So you have this sphere bundle over the boundary of this at infinity, which is where the operator is characteristic. Okay, so first of all, we notice that if U is some kind of tempered distribution, it's a solution to Laplacian plus k squared U is in Schwartz class. Classical ellipticity tells us that this is a C infinity function. We can just forget about the classical wavefront set, which is a measure of the singularities of the function in the interior. But here, for example, we have a function e to the I k omega x. That's a solution of our equation, but it doesn't decay at infinity, and it oscillates in directions that depend upon the point. It doesn't satisfy the outgoing radiation condition. The scattering wavefront set quantifies the oscillatory nature of solutions to this equation and their decay. Okay, so first of all, we have to define what we mean by the scattering singular support. So we pick a point at infinity. It's not in the scattering singular support of U, provided there's a smooth cutoff function such that which is 1 at that point at infinity. And if I multiply my solution by that phi, what I get is in Schwartz class. So in that direction, the thing is rapidly decreasing. That's what it means to not be in the not be in the scattering singular support. Okay, so if a point is in the scattering singular support, that when I localize it near that point at infinity, it's not a Schwartz class function. So I'd like to quantify this in terms of the failure of decay and the oscillation at infinity. We split the scattering cotangent bundle into a radial set, which is just omega dot xc, which I said before was the symbol of d by dr, and just the difference, which is the tangent directions. We'd like to know the frequency. We'd like to know if a frequency, tau naught, mu naught, is in the scattering wavefront set. So what we do here is we do the same thing. We pick something that localizes near tau naught, something that localizes near mu naught. We use this data to define an operator. So that is, we take the Fourier transform, again, in the distributional sense of this function localized near the point at infinity. I multiply it by these two cutoff functions, take the inverse transform, localize again. So if this operator applied to my function gives me something which is an x to the L times the mth Sobolev space. That is, it decays like x, like the distance to the bound, 1 over the distance, 1 over r to the L power, and it's got a certain number of derivatives, then it's not in the scattering wavefront set at that frequency and that decay rate. Okay, so let's do an example. The scattering wavefront set's always contained in this characteristic variety. Let's take our plane wave solution. We compute its scattering wavefront set. It looks like theta, which is the point at infinity, and then it's a curve that goes from k cosine theta minus phi minus sine theta minus phi, and theta goes from minus pi to pi. So it's a curve at infinity that goes from the top of the sphere to the bottom of the sphere on both sides. Goes around both ways. Okay, so Melrose establishes some very important properties of this thing. Hard to understand exactly what it is, but let's see what the properties are. It's always a closed subset of the characteristic variety. The symbol of the operator defines a Hamiltonian vector field in infinity. That's what it looks like. It's a vector field on this cotangent bundle. The scattering wavefront set at smoothness m and decay rate L, it's a union of closed trajectories of this vector field. So this is like the classical propagation of singularities theorem for hyperbolic equations. That this, whatever this thing is, it's a union of closed trajectories. This vector field vanishes at, over each point at infinity, it vanishes at exactly 2 points. So these are called the radial points. The radial frequency is plus or minus k, the tangential frequency is 0. And omega is just a point on the boundary. And every trajectory of the Hamiltonian vector field will converge to the radial set as the time parameter goes to plus or minus infinity. If this scattering wavefront set does not intersect one of these radial sets for an L less than minus a half, so that's saying it doesn't decay that fast at infinity, then these points must actually be limit points of trajectories. So I have these special points. And if the special point is in this wavefront set, but the solution doesn't decay faster than my critical rate, it decays slower than my critical rate, the only way that can happen is if these points are limit points of trajectories, complete trajectories that go from R plus to R minus. And finally, it is possible if they decay at if it decays at a faster rate for some m and L greater than negative a half, then in fact, the scattering wavefront set is disjoint from that radial component altogether. So again, this is like Relich's theorem that said, if it decays faster than 1 over R to the n minus 1 over 2, then in fact the solution is 0. This is sort of a microlocal version of that statement. Okay, well this explains why Isozaki's condition is enough, because his condition implies that the scattering wavefront set intersect with the minus, RK minus, the incoming part is empty. This then implies that the wavefront set must be contained in RK plus, because if it weren't contained in RK plus, there would have to be a trajectory. If there were a trajectory, a non-trivial trajectory, it would have to have a limit point in RK minus. So there would have to be a point in RK minus. I'm getting there. Okay, so this is why localizing to a half space is enough. Okay, and in fact, okay, so Melrose also proved the version of Relich's theorem, which was that if you have a solution, a global solution, its wavefront set at the minus a half decay rate is contained in the incoming radial set, and in fact the solution is identically 0. Okay, I think it's too technical to go on from there, and I'll just say, okay, so we then wanted to solve a problem. So I picked this problem. This is the easiest non-trivial problem. It's two semi-infinite waveguides that meet upon a common perpendicular line. The wave numbers in the channels are different and bigger than the background wave numbers, so you get waveguide modes in that case. I don't know what that is. We construct the fundamental solutions. We write the solution on the left and the right side in terms of the left and the right fundamental solutions. We can write these fundamental solutions as the background free space fundamental solution plus a perturbation term. The perturbation term satisfies that PDE, which tells you that actually the perturbation term is 2 derivatives smoother than the free space solution, which is good. We actually compute it using the Fourier transform. We use this great fact that for an ODE, you can write down a formula for the resolvent, which is very useful. Okay. We have to deform our contour. I think in the end, we get integral equations that look like that. So this is like a miracle. This is one of these things where God hands you something and you're really surprised you got it. The integral equation simplifies to this identity on the diagonal and these two operators off the diagonal. And you want to solve that kind of an equation. You have remarkable asymptotics. Okay, so here well, as I said, you need to find Banach spaces on which the thing is a Fredholm operator. And so we define these Banach spaces in terms of an algebraic rate of decay and an exponential rate of decay of the analytic continuation. We won't really discuss that part. It's really this algebraic decay which is important here. And the interesting thing is those two operators, which are off diagonal, they interchange the two Banach spaces. Again, this is sort of a miracle because if you didn't get the opportunity to interchange two Banach spaces and you had to find a space that these operators map to themselves, I'd still be looking 3 years later because I don't think there is a space that these operators map to themselves. Okay, so it turns out this equation is Fredholm of index 0. I don't know whether these mappings are actually compact, but you can still prove it's Fredholm of index 0, and you can prove that it has a unique solution. So let me just show you some examples. So I have another collaborator, Tristan Goodwill, who used his complexification trick and bravely solved the equation. So this is the incoming field. It's a waveguide mode from the left. This is the total field. So it's broken up into the waveguide portion and the radiated portion. So you see there's a tremendous amount of radiation. You can see a little reflected wave there. You see a beautiful transmitted wave there. Tristan he's a brave guy. So then he thought about, what about a splitter, a Y splitter? So that requires a lot of effort to put something in the middle there. So the previous problem I showed you took about 10 minutes to compute. This took about 10 hours to compute. And all the computation was really for that little piece in there. Those are the waveguide modes for the right-hand side. So I said to Tristan, we can compute the scattering matrix. Can you figure out what the incoming field should look like to make all of the energy go into the top branch? So he did that. So you can actually sort of design components using this kind of numerical work. And this is kind of amazing because 98% of the energy goes to the top branch, and there's only like 2% radiated power, which was, again, nothing was done to try to reduce the radiated power. It just happened to be almost negligible. Then he thought, okay, let's try a bent waveguide. I don't really have a chance to explain it, but actually a bent waveguide is a lot harder than two parallel waveguides. And then he thought, well, what if I put Dirichlet boundary conditions on the edge of the pipe and just don't make the pipes fit? So he did that one. And then he thought, well, what if we stick some thing at the end? He took this idea of decomposable scattering problem very seriously. Anyway, thank you very much for your attention. And hopefully we'll have a lot more years together.
Questions?
So you mentioned the quantum mechanical scattering problem. There, the basic scattering problem is that you have molecules going in, and you want to show you all that happens as different other molecules come out.
Right.
And the issue is to compute if you've got hydrogen and oxygen in the form of water, is it going to come out as H2O2 or something else?
Uh-huh.
So the problem classical problem there is that if you do have molecules going in, you will get molecules coming out. That's asymptotic completeness.
Right.
But actually computing how much goes into this now, that's still an unresolved issue. Part of the difficulty was that people went from the equations, which are energy equations, they take the Fourier transform and they look at the propagators, and they solve it using dynamical methods, but they're unable to compute the actual what goes into which channel. So now the analog for you, I understand, would be as if you drive one channel,
Right.
much goes into the other channels.
Right.
And you're saying, at least in the case where you have just a single split, you're able to compute how much goes into each channel.
Well, for this problem, this 2D problem, you can compute. We don't have. I don't know how to estimate that. That's obviously a very good question. How is there some kind of theoretical estimate for what goes into each channel? And I don't know how to do that, but we can certainly compute numerically what comes out in each channel. And that's how he did that thing where he put all the energy in the top branch. He just computed the scattering matrix. He just maximized the power in the top branch. And and actually, he just computed the channel to channel. He just used the channel to channel part. So he didn't try to control the radiation. It just so happened that very little radiation existed for that particular choice. That's just something surprising. Maybe there's something really interesting there.
What I'm really interested is that initially the analysis of asymptotic completeness was done using these energy equations, these elliptic equations.
Right.
People like Fredholm and people like that, but they failed.
Right.
Because the equations they got, they could not prove Fredholm. They were
Right.
specious singularities came in.
Uh-huh.
So people went to these time-dependent methods,
Right.
which sort of killed the problem in an unfortunate way, because you want to compute the actual scattering matrix.
Right.
But the message from that is that you just have to wait long enough, and then you see you never learn anything about it. So,
But you don't know how long that is either.
and what I'm really raising is it possible for you to use the methods to begin to compute the scattering matrix for mechanical problems, even three bodies?
I haven't thought about it, but it's potentially possible. I mean, I would tell you something. Actually, there's a sort of a little hint of that in our analysis, which is this: that if I have two waveguides that meet at right angles like that along a common perpendicular line, and then what I do is I introduce this artificial boundary, and I solve this transmission problem on the artificial boundary. And I was just doing this blithely, not really thinking about it too carefully, and I realized, and I prove all these amazing facts about the kernels along that line. And then I thought, well, what if we just take a skew line? And I discovered this very unpleasant fact that the kernels of the perturbation of the free space operator, which you need to formulate the equations, the kernels behave very differently on a skew line. The normal derivative so the normal derivative on this line will decay one order faster than the kernel. Along a skew line, it doesn't. It decays at the same rate as the kernel. So then I'm in this problem, in this situation where I absolutely don't know how to write down function spaces where I get a Fredholm operator, where I even get a bounded operator. I don't know how to show, I don't know how to find a space where this, just say the single layer operator along the line maps a space to itself on an unbounded boundary. You have to include oscillation. Now, it's in quantum mechanics, they had this other trick, which is this complex scaling trick, which is closely related to this complexification I'm talking about. And I would say it's possible, and I think actually in our problem, what we're going to do is we're going to try to prove that, first of all, we're going to prove that if you complex scale the equations, they become Fredholm. I think that's easy to prove. The problem just is to prove that when you go back to the real space, the limit of the solutions is the solution to your original problem.
Usually complexification in quantum mechanics addresses issues like absence of singular spectrum issues, but not dynamical issues like computing the scattering matrix.
Yes, but it could. But I mean, if the issue was a lack of Fredholmness of equations and things like this, it could very well be that you regain that by complexifying the coordinates, solving it in the complexified space, and then proving that as you go back to the reals, the solution converges. It's like another limiting absorption principle. That's perfectly plausible to me that might work. I believe that for my problem that will work. I haven't done it yet, but.
Okay, well, for the interest of time, let's.
Time and sanity. Time and sanity. And sanity.
And it says that.
Time and sanity.
Okay, we're fine. We're fine. Okay, we have Ken. Thank you very much, Charlie.